Good afternoon, CSSconf. My name is Elyse, and I work on the front-end core team at Indeed.com, which is the world's #1 job site. Today, I want to talk about our working theory of modern web development, components. But let's start with another theory, the law of gravity. Newton's law of universal gravitation states that gravity, a mysterious, unexplained force, works on all objects in the universe. Objects attract each other based on their mass and distance. More massive objects attract each other with a greater gravitational force. And this is what sends the planets in their great orbits around the sun. Newton's Principia Mathematica was published in 1687. After its publication, the greatest mathematical minds in Europe used Newton's law to discover and prove truths about the celestial world. Astronomers worked out sophisticated descriptions of the orbits of the planets, called tables. And tables showed where the planets should appear in the sky, and the calculations always matched the real observations. But over time, small discoveries began to accumulate that didn't make sense. The first observation of what would later be known to us as the planet Uranus didn't fit into the math. Some planets, like Jupiter, seem to be moving faster in their orbits than in previous observations, and that couldn't be reflected in the math. Many began to wonder if Newton's laws were not universal after all, if there was a flaw in the theory. But not Urbain Le Verrier. Le Verrier was a French astronomer who, while not an excellent observer, was an unparalleled mathematician. In 1846, he posited that Neptune had to exist, based on the math of the orbit of Uranus. Le Verrier wrote to an astronomer here in Berlin, Johann Gottfried Galle, with the predicted coordinates, and the very same night, Galle observed Neptune within 1 degree of where Le Verrier had predicted it should be. In response to claims that Newton was wrong, he wrote, "If the tables do not strictly agree with the observations, we will certainly not be tempted into charging the law of universal gravitation with inadequacy." In other words, even if some observations don't match the math, we shouldn't immediately say the entire theory is wrong. In Le Verrier's eyes, there was no need to toss out gravity altogether just because there were some gaps in our knowledge. At the time, no one even knew how gravity worked, even though the math made sense. Le Verrier believed that as time passed, we would improve upon our understanding. Over the past 20 years, our understanding of the world of front-end development has changed. We've been iterating constantly on our working theory of how to design and code for the web. It's fitting to talk about this history at the 10th and last CSSconf. When CSS Zingarten came out in 2003, we were making web pages, documents, and the browser wars in the 90s had left us with conflicting standards. We collectively fell in love with CSS. And then came jQuery and the separation of concerns. Reusability with CSS classes meant being able to change our HTML without touching our CSS or JavaScript. And as we began to build web apps, these complex, interactive structures, our attention turned to tools that would help us write more flexible code. We learned responsive web design, SAS, complex CSS architectures, and new JavaScript frameworks. In the 2010s, we gained powerful tools like NPM, Webpack, and React. On the design side, we moved from Photoshop to tools like Sketch, Abstract, and Figma that are slowly narrowing the divide between design and code. We were looking for better tools for reusability, clarity, and maintainability. We've used these tools not just to create solutions to our problems, but also to create new tools. And these tools are changing the way that we conceptualize our work. We're building on what we learned previously and filling in the gaps and the unknowns. In the early 1850s, Le Verrier was calculating the orbits of every single planet. He intended to create a complete set of tables that showed where the planets would be in the sky at any given time. First, he mapped out the actual orbit of the planet based on observations. Next came calculations. What did Newton's laws predict the orbit should be? And the observations and the calculations should match. Venus, Earth, and Mars were all correct. One, though, obstinately refused to conform: Mercury. Mercury's orbit shifts forward incrementally each time. As the planet wheels around the sun, its orbit makes its own gradual orbit, creating a flower petal effect. This shift is too large to be explained only by the pull of Venus and Earth's gravities. Leverrier, in his book-length report on Mercury, wrote that the likeliest solution was a planet between Mercury and the sun, providing an additional gravitational pull. He named this possible planet Vulcan. Vulcan would orbit so close to the sun, you wouldn't be able to see it in the daytime. And like the sun, it wouldn't be in the sky at night. In the years after, astronomers all over the world observed Vulcan. In July of 1878, a total eclipse crossed America's west from Montana to Texas. Because the sun would be obscured, getting a clear observation of Vulcan was the biggest prize. During the eclipse, an American astronomer, using a small telescope, a setup of cardboard circles, and a sharp pencil, plotted the transit of an object as it moved across the sun. He and many others believed it was Vulcan. The math worked out. It fit neatly into the explanation of Mercury's orbit. But over time, observations of Vulcan dwindled, and people began to doubt that it existed. And for years, the question of Mercury's orbit created discord between astronomers. We know now that Vulcan doesn't exist, but people kept discovering Vulcan because it fit into their understanding of the world. The limitations of their tools and knowledge at the time kept the answer just out of reach. As an industry, we too had a gap in our knowledge. How do we build for maintainability and scale? We agreed that we're no longer building pages, we're building systems. We agreed that we need components that are independent and reusable. We agreed that we need a single source of truth in code for an easy authoring experience. But how? Based on our experience of the world, we tried varying solutions and tools. For some, CSS tooling and methodologies. For others, JavaScript, CSS, and JS. New ideas are often criticized and dismissed. CSS and JS was controversial. It still is. Putting our CSS back in our HTML was rejecting that separation of concerns that we had learned in the past. You might build components for a web app with a JavaScript framework. Maybe you work on a component library or design system. Maybe you use functional CSS, or Sass and BEM, or styled components. Maybe you use plain CSS and vanilla JavaScript. Maybe you feel stuck with your legacy code base, your cardboard circles and sharp pencils. We're heads down in our work, trying to find solutions. We're not always thinking about the big picture. And this causes conflict among us as we struggle forward to a better understanding. But we're still working towards the same core idea. So, what is our working theory of a component? And how can we solve for the values of consistency, cohesion, reusability, authoring, maintainability? How do we test this theory with the tools that we have today? We know that a component needs to be three things. Eins, easy to reason about. Zwei, context agnostic. Drei, independent and isolated. First, a component must be easy to reason about. Being easy to reason about isn't only the amount of code or size or visual complexity. Something that looks simple can be deceptively complex, and some components that are hard to code are not difficult to think about. A component that has too many variants will be more likely to have bugs. It will be hard to test if all the variants work or when they get used. You might have too many props and options or different styles for the component in different contexts. On the other hand, too few options mean a component is pointless. There's a spot that's just right where the component is used for one or a few cases with enough options to make it flexible. Complexity in a component may come from design or business requirements, or it may build up over time as developers add features or designs change. If your project is like mine, where many other teams use components, sometimes those teams' needs diverge. At some point, you may need to split a component up into smaller pieces that are easier to conceptualize. And if there are common combinations, you can create shared parent components for those. For component libraries, getting other developers to use components relies on their ability to understand what the component is for. Often, I see developers say that they couldn't use a component because it didn't offer the right options that they needed. Sometimes they're right, but often they didn't recognize the option was available. A component must have all of its options and variants well documented in code, examples, and tests, so that it's discoverable and easy to understand. So a component that is easy to reason about should be flexible enough to support its use cases without being unwieldy or confusing. Second, a component is context agnostic. Components promise us reusability. We want to take a button or card or comment block and use it all over our projects. To be reusable, a component must be context agnostic, meaning it shouldn't need to know where it is to look or behave properly. To function properly and consistently across contexts, a component should not have logic that controls functionality outside of itself. It should receive data down and send actions up. Take, for example, a call to action component that has a button. When the button is clicked, a modal opens. It would be easy enough to write code that pops a modal on click, and that will work until we want some other functionality. So instead, the button should just bubble up an event. I got clicked. And the application can determine what to do when that event occurs. Styles for a component should also have a single source of truth. Whether you namespace CSS with unique classes, generate your styles from JavaScript, or use functional CSS, you know what belongs to the component, what doesn't, and where to find it. Don't rely on the markup structure, the contract between the parent markup and the component, to define the component's styles. A component should have styles that are flexible enough that it can live anywhere, in a full-width parent, in a sidebar, or on its own. And you can let parent components control the layout, like widths or grid. If a component is supposed to look or behave differently in different contexts, make sure the logic behind those changes is well defined. It's possible the component needs to be split into two, or sometimes the best solution is not a shared component at all, but implementing that feature as a one-off. So a component that is context agnostic will be reusable and flexible. Third, a component is independent and isolated. To be context agnostic, a component must be independent and isolated. But isolation of functionality and style gives us more than just the flexibility to use a component anywhere. An independent component should have good defaults, like default text, accessibility settings, and empty states. It should just work straight out of the box. This means it needs to import all of its own dependencies. We're familiar with this pattern in JavaScript, importing packages as needed. And this gives you confidence in what is there and makes it easy to test whether or not an imported file is actually used. A component being independent and isolated means it will look correct in an isolated environment. It cannot rely on the presence of styles from a parent container or a global page. Completely isolated components means you also have the ability to test with confidence. You can generate each component into its own page by itself and run visual regression and unit tests. Isolation for testing means that your component tests only itself and doesn't rely on other page functionality to work properly. We know then that any bugs we catch in that isolated environment are in the component, and bugs elsewhere are byproducts of how the application and the components interact. And this makes us confident in the component's quality. Developers should trust that components won't break their pages. And it also means we don't have to hobble the creativity of our designers for the sake of code predictability. If you have components that are understandable, independent, and can live in any context, you can now use other components by composition. A component can import or reference another component in its markup. It may make style tweaks, pass props, and change options. Data can be changed in child components, and events and state passed back up. And so this is our current theory about the world of modern web development. Using the tools they had and what they observed and the knowledge they had, Vulcan was the best explanation astronomers in the 1800s had for Mercury's orbit. And it would take almost 60 years to add new information to the theory. It's 1913, and Einstein is working on his theory of general relativity. He does a calculation to see what his math predicts for the orbit of Mercury, and it fits. The core concept of general relativity is that space and time can be changed by the presence of matter. A vast mass like the sun distorts space-time, so Mercury's orbit shifts because that's the path it has to take through the curved space-time around the sun. Without curved space-time, you need some other object's gravity to pull on Mercury. With curved space-time, Mercury's observed orbit makes sense. But Einstein didn't disprove Newton's law of universal gravitation. Gravity still exists. The tables of planetary orbits that Leverrier calculated in the 1850s are still accurate. General relativity updated our understanding of the world. It filled in some gaps, gave us better measurements, and strengthened the theory that came before. Many astronomers worked as observers. They saw and recorded how the world really was. Others, like Leverrier and Einstein, worked as mathematicians, pushing at the edges of our theoretical knowledge. And you get to do both. You might not feel like you can innovate if you work for a big company or on an old tech stack, but the majority of us don't get to use all the new cool technologies. I've worked on this theory of components in everything from PHP and SAS to React, and even plain CSS for Java templates. And even without the newest tools, we are applying this theory to our work. Your project has limitations and constraints, the laws of the world. We know what we want components to be, our theory. So as you write code, how do you know if your component fulfills the theory? Your particular application of this theory will depend on your particular project's requirements and technical constraints. At Indeed, my team put together a checklist that lives in our project's contributing docs and that describes how we build components. Defining what a component should be gives you a tactical way to test your results and the theory. It outlines the 3 high-level concepts I spoke about: being easy to reason about, being context agnostic, and being independent and isolated. But it also contains a much more concrete list of what a component must do. Here's some examples. To be easy to reason about, a component must have written design and usage documentation, as well as code comments for all props, options, and variants. It must have unit and visual tests so we can make and verify changes safely. And it should have limited variants that fulfill real use cases with examples of how and when to use them. To be context agnostic, a component must work in all supported browsers and devices, including touch, mouse, keyboard, and assistive devices. It should meet accessibility standards, and it should look and function correctly in both left-to-right and right-to-left languages. It should have no external layout properties like grid, float, or even margins that would keep it from being used in a variety of contexts. And it should receive data down from the parent or page and bubble actions up. To ensure a component is independent and isolated, it must work in an isolated environment. It must define or import all of its own dependencies, including JavaScript and styles. And it should define the component namespace or key selector only one time in one place. It should have appropriate default text, empty states, and error states. And it should only affect itself and not rely on other components or the page for functionality. And this checklist makes it easier for anyone who works on components to do the right thing. With a checklist as a reference, we can be sure we've done everything necessary to make a component that will work as expected and be a valuable part of our library. We keep the theory and promise of modern web development close at hand in our everyday work. As we build, code, test, and try new technologies, we are observing how the theory works and improving our understanding. After formulating the theory of general relativity, Einstein pondered what would happen when a huge object in space was disturbed, like 2 black holes colliding. He predicted that a cosmic event that disturbs the fabric of space-time with enough force should produce ripples in gravity. Scientists didn't agree. Many believed that these ripples were just artifacts of the new math, that somewhere the calculations were wrong. Even if the ripples were real, they would be so small by the time they got to us, we wouldn't be able to detect them anyway. At the time, many scientists didn't even believe black holes were real. This theory explained many things, but it also opened up new questions. Over the last half-century, there has been an experimental quest to detect these gravitational ripples that Einstein predicted. An international team of scientists has built a pair of colossal gravity wave detectors called LIGO to try and detect these ripples. LIGO, the Laser Interferometer Gravitational Wave Observatory, took 50 years to build and cost millions of dollars, and the LIGO teams weren't even sure they would detect anything when it was done. People questioned, doubted, mocked them. Yet the LIGO teams persisted because it is crucial to think beyond today's understanding of the world. Out in deep space, 1.3 billion years ago, two black holes circle each other, churning up space and time until they crash and merge into one enormous black hole, an event outputting more than 1 trillion times the power of 1 billion suns. The black holes collide in complete darkness. None of the energy exploding from the collision comes out as light. That energy emanates as waves in the shape of space-time, as ripples in gravity. An astronaut floating nearby would see nothing, but the space around her would ring. When black holes collide, they make a sound. In December of 2015, almost exactly 100 years after Einstein presented general relativity, LIGO detected that collision. We heard two black holes collide. LIGO's discovery verified general relativity as fact and changed the way that scientists understand the universe. LIGO not only changed our working knowledge of the world, they accomplished one of the greatest feats of modern science. And yet again, we have new questions to ponder. Our work may not seem so grand. What could be grander than black holes, planets, celestial motion? But even firmly planted in our earthly work, we too can think like scientists, continually working to expand our theory, confirm it, and strengthen it. When we build new applications, try new technologies, give conference talks, create libraries and design systems, we are observing and calculating. What we learn will add to our theory, help us create even better tools, and propel us forward into a new world. So as we work together today and tomorrow and in the months and years to come, keep thinking beyond today's understanding and on to tomorrow's. Thank you.